What's that? Okay. Okay, so I'm Kyle Fates, and I'm with the School of Computing at Weber State University. I've been coming to SAINTCON for, I think this is my 4th year now, and I've been doing trainings and presentations on Wireshark for 3 years at SAINTCON. If you've been to any of the previous Wireshark trainings I've done at SAINTCON, then you'll either be bored or you'll find out that you didn't pay very much attention last time, or a year's a long time, you might have forgotten everything. So it's largely the same stuff that I've talked about before. And so just a disclaimer there, if you've already listened to this talk and you want to step out, that's fine. If you're coming in, make sure you get the files that we're going to be working with. You need the Wireshark program, which is available at the first link, and you need the capture files, which is the second link. And this gap here, there's actually an underscore that you can barely see. So make sure you include the underscore in the URL. We're going to be focusing on using Wireshark to analyze network traffic, not on using it to capture network traffic. So Wireshark is capable of both capturing the traffic and analyzing it. But when you capture the traffic, you have to worry about what are the legal ramifications of doing that. Do you actually have the permissions you need to capture that traffic? And if you're using this at work or on your own, at home, whatever, just make sure you know what those legal ramifications are, what your company policy is in terms of what traffic you can and cannot look at. We will provide this is an introduction level class or presentation training. So it's not going to give you, if you're already familiar with Wireshark and you're hoping to go deep into its other features, this isn't the training for that. This is meant for people who've never used Wireshark before or who have some familiarity with it, but have just dabbled with it a little bit and want to know a little bit more. That's what the target audience is. We will provide some background knowledge in terms of network protocols and what they look like, how they're used. But again, we'll consider that required knowledge coming in. So a little bit of a review, and happy to answer any questions, but we won't focus on understanding the protocols. We'll focus on using Wireshark to look at and analyze the network protocols. We'll talk about a little bit what Wireshark is, where and how to sniff or capture packets. I told you we're not going to be doing that, but we will talk about how you would do that. And we'll take a look at the interface and some of the features and some of the customizations you can make. We'll get into network protocols and actually analyzing them with Wireshark, and then finally some more advanced uses as time allows. It's going to be very hands-on, so if we go back here, make sure you have the materials you need to participate. That's the way you'll get the most out of this training, is actually following along, doing the activities, asking questions, so that you maximize your time here. I teach, so I mentioned I'm from Weber State. I teach up there in our programming classes, our network security classes, and so we have a whole class dedicated to Wireshark, an entire semester, 4 credit hour class, and which means in 1 week, 4 hours of class time, that's what we're getting in this training, and then times that times 15 weeks of all the stuff we could talk about with Wireshark. So that gives you an idea. We're just scratching the surface of what we can do here. Okay. So let's talk about what is Wireshark. How many of you have used Wireshark before? Okay. How many of you would say you're comfortable with Wireshark? Good. So I was a little bit scared at first when everyone said they'd used it. I was like, oh no, you're all gonna know all of this stuff. But I feel better that most of you aren't comfortable with Wireshark. You've used it, maybe you've heard of it, but not a lot. So Wireshark is a way to look at the network traffic that's flowing across our Ethernet cables, going across our wireless airwaves. It's very versatile in the types of packets and protocols it can work with. And what do I mean when I say it lets you look at the traffic? It lets you see the actual ones and zeros, the bits and bytes that are being sent when you connect to Google, or when you open up an SSH connection, or when you launch a Metasploit attack on another device. All of that's creating traffic across our network, and Wireshark lets us see that traffic. How many of you are participating in the Hackers Challenge game? Okay, so an example of how Wireshark could help with Hackers Challenge. I'm playing Hackers Challenge, and I was doing I forget the name of it, but the one get bashed by a pipe was the hint or something like that. And it has you download a bash script and install it. Well, so I downloaded it, and if you, like me, just tried a simple download, you'll notice the script says something like sleep, some number 3, and then echo, not here, or something like that. Right? Well, I was confused by that because obviously there should be more. So what did I do? I turned to Wireshark, and I said, my program told me this was all that was there, but maybe there's something behind the scenes. And when I fired up Wireshark and captured the traffic as I was actually downloading the script, then I saw, oh yeah, there really is more here. And there's a saying in the network world that the packets never lie. What the actual packets on your network are, and seeing that actual data, that's your ground truth. And then what the application does with it or what it says about it can sometimes lie, but the packets never lie. So you might have a network like this. This is a fairly simple network where we've got a couple routers, a wireless router, a couple switches with maybe some network segmentation here to maybe these ones are the ones that we want available externally, our web server or something like that, and these are our desktop workstations. Okay. The reason I have this picture is to talk about how to capture. I said Wireshark can see the packets across your network, but it can only see packets that are going across your network. If you are running a Wireshark instance on this laptop here, it's only going to see the traffic going here or going here. It's not going to see traffic from N10 to N8 because it's not on that path. If it's not going to see traffic from N2 to N8 because it's not on that path. So that's the first thing to understand about Wireshark is it will show you all of the traffic, but it only shows you the traffic that's actually there, the traffic you can actually see. And so that becomes an important consideration when you're troubleshooting a problem and you're using Wireshark and you want to know, why isn't my desktop able to talk to our intranet server? If you're trying to capture from someone else's desktop, it's not going to work. If you're trying to capture here at the router, that will give you the best picture of seeing all of this traffic. I don't like to talk too long without doing something interesting, so let's actually bring up Wireshark. So here's Wireshark. It's kind of hard to see the interface. Let me use our magnifier app here. Okay. So now, if we, at the top of the screen will be a larger view. Is that large enough? Probably not large enough for the very back, but large enough for, the first half of the room to see these menu items and stuff now? Yes? Okay. So you start Wireshark, and if you have it configured correctly, you will see some interfaces listed here. You'll notice my list of interfaces is blank. Normally, you'd have your LAN, your local area connection, your wireless connection, maybe a USB connection or something. You might see a whole bunch of interfaces here. If you're running in Linux or a Mac or Windows, the interfaces might be slightly different, but there'll be a list of the different interfaces that you can capture traffic from. You have to have administrative privileges to do that, or you have to set it up so that it can access those without those privileges. And I haven't done that on this machine, because I don't usually capture traffic on this machine. So it doesn't have the permissions, and it doesn't have any interfaces it can work with. Like I said, we're not actually capturing traffic in this training, so if your list is empty as well, that's fine. If you have things listed here, that's fine. Just wanted to show you, this is where you would select an interface to capture traffic from. And then there's this extra thing, using this filter. So when we capture traffic, sometimes we want all of the traffic, and sometimes we just want some of the traffic. Like maybe we just want TCP traffic, or maybe we just want SSH traffic, or maybe we want traffic to a specific IP address. We can limit that in our filter here. And the little bookmark has some that are already built in that Wireshark says, hey, these are useful, people sometimes like them. So I talked about, you could do it by a specific IP. So we could say, this one here. It says IP address 192.0.2.1.1. And when I click on it, it sets this capture filter of host 192.0.2.1. And if I applied this capture filter when I was capturing, then if the IP address didn't match this IP address here, it wouldn't capture the traffic. And we would exclude traffic that wasn't destined for this host. Now, I don't recommend using a capture filter unless there are legal reasons for doing so. So if you need to restrict what packets you capture, then yes, use a capture filter. But most of the time, it's better to just capture all of it. That way you don't miss something. Because you might think, oh, I've got a problem with SSH. I'm not able to connect to my desktop at work. I'm going to use Wireshark. And I'm just going to capture the SSH traffic because that's where my problem is. Well, if you do that and you do a capture filter so that it's only capturing the SSH protocol, and the problem turns out to be you couldn't resolve the domain name of the system you were trying to SSH into, or there is another system creating a denial of service, but it wasn't doing SSH protocol, it was because it was flooding your network with Samba packets. If you excluded all of that traffic, you won't see it. So it's usually better, unless there's legal reasons not to capture all of the traffic and then go back and limit what traffic you look at. Because you don't necessarily want to look at all of it, but you want to have it all available in case you need to look at it. Okay, so let me show you some tricks here. When we're using Wireshark, if you look down in this corner, so the bottom right corner, and I've got it big up here, but it's actually down here, it says profile. And in this case, profile default. And if you click on that profile, there's some other options like Bluetooth and Classic is what I have currently available. Profiles can help you manage your interface. So if you start using Wireshark a lot, you'll find that certain customizations work well for certain situations. Like, maybe I want to have a set of capture packet filters available when I'm working with FTP traffic. But I don't need those same filters available when I'm working with HTTP traffic. And profiles is the way to do that. You can customize your interface for the different tasks that you're working on. If instead of clicking on the profile, if we right-click on it, then we get a slightly different menu where we can manage profiles or we can create a new profile directly. I'm going to click Manage Profile here. And it brings up a new window with the list of profiles, some buttons down here to add or remove a profile or copy a profile. And I'm just going to add one, and let's call it Demo. And I like this, especially when I'm presenting, because if I work in my demo profile and make changes to how the interface is configured, it won't affect any of these other profiles. And so I can completely mess things up and break them, and at the end of the day, just throw away my demo profile and go back to my default settings. So take a minute, create a profile, at least one. Maybe you want to call it demo or training. And once you have created it, select it, click OK, so that you're actually using that profile. And you should see it down in the bottom right corner with the profile name. Questions on how to create the profile or why we create a profile? Okay. Does anyone not have their profile created yet? All right. So most people are ready. Let's clear that out. Hopefully you've had a chance to download the files now. Let's go ahead and open a capture file. So we go File, Open, and wherever you downloaded it to. And the one we want to open if you downloaded the entire zip file, it's in the basic folder, and it's the baseline.pcapng file. Okay, so in the downloaded capture zip file, you unzip it, in the basic folder, there's a baseline pcapng. That's the one that we're going to be working with for 90% of this training. When you open it up, now our interface changes. We no longer have the list of devices to capture from. Try and keep my mouse in a spot where it's useful. Instead, we have this list of IP addresses, timestamps, protocols, some information. And these is a summary of the packets that we've captured, one per line. And then underneath that is a detailed view of those packets. And as I change which packet is selected, this detailed view in the middle section here will change. So right now, the first packet's selected. If I select the second packet, let's do one that's a little bit completely different. There we go. So I select the fifth packet, and these details change. So both the middle and the bottom section are a per packet view. And it's showing the fifth packet, what are its details, and what are the actual bytes of that packet. Let's fix one thing here. Okay, so I'm going to keep my magnifying glass up here because the file menu sizes don't change, but I can increase my font size of my display so that most of the time you don't have to look at the magnifier. Control plus will increase the font size, and there's other ways to do it, but that's how I usually do it. That's a profile setting. If I switch my profile back to default, it switches the display back to unzoomed. So like I said, create a profile and then start customizing it. And if you like those customizations, keep it around. If you don't like those customizations, throw it away, create a new profile. Okay. Whoops. So these three windows under our view are the three that we just looked at: the packet list, the packet details, and then I accidentally just unchecked this packet bytes. So it went away. Now we have them all three back. Where'd this go? I like to have all three available. The list of packets, a detailed view of what the packets are, and then the actual bytes. If you don't need one of them, get rid of it. Right? I like to keep them around. Up here at the top, it's got this bar that says apply a display filter. Yeah, go ahead.
Is there a time that you use the bytes?
Yes. So I use the bytes often, and the bytes will show you this is the actual data of the packet. And so, for example, I talked about downloading the bash install script, and what happens is when I looked at those packets and looked at the bytes, they were very different than what the final file ended up being. And so, that was an example of the binary data, or interpreted as ASCII, was actually very useful in terms of showing me, hey, the final product isn't matching what was originally being sent. So we talked about that you could use a capture filter, and I said don't do that in general. But you can do a display filter, and right here is where you do the display filter in this bar at the top. And I highly recommend you use display filters. They're going to be very helpful in finding what you're looking for. And they're very powerful. There's way more that you can do with a display filter than we can talk about in 4 hours. So let me just show you a few tricks. The first is the built-in display filters. So you click the little bookmark-looking icon right next to the display filter bar, and it's got some built-ins, just like we saw with the capture filters. And they're very similar in terms of what's built in. If you want to look at a specific IP address, you can do that. If you want to exclude ARP traffic, you can do that. The syntax, you'll notice, is different between capture filters and display filters. It's another good reason not to use capture filters, because then you don't have to learn 2 different filtering syntaxes. You just focus on the analysis filters and ignore the capture filters. So if I want to only see traffic that's to or from 192.0.2.1, I put in this filter, ip.adder =, the IP address I'm looking for. And you'll notice what that did to my display. They're all gone. There are no packets in this capture file that have that IP address. So let me clear that out and get one that so if I expand out these columns so I can see the full IP address, I can see the first couple packets, some of them 192.168.3.112, and some of them are 192.168.3.1. And if I scroll down through all these packets, I can see there's lots of other IP addresses as well. Well, if I'm troubleshooting a problem and I know, or I think the problem's related to a certain IP address, I can get rid of all this extraneous stuff. Say I only care about IP address equal to 192.168.3.112. And now, any packet that doesn't have that IP address as either a source or destination address is gone from my view. It's not gone for good. We can always go back if we find out the problem was somewhere else. But we don't have to focus on it when we're trying to pick out this needle in the haystack. Yep. Is that better? You bet. So that's great. There's these built-in filters that can get you started, but there's only 10 filters listed there maybe? Oh, a few more at the top that were getting cut off by my magnifying glass, but not a ton. Here, let's actually do this one for a minute. Except I can't. I'll do it directly. So we could do a filter based on a protocol we're interested in. And we could say, well, only show me the HTTP traffic. And that's nice. It got rid of all those DNS packets. It got rid of all the ARP packets, everything else. And is now just going to show me the web traffic, the HTTP traffic. Okay? But what if you want more than this? this list, like I said, is fairly limiting. If you click over on the right-hand side, there's this expression button. And so when you click on that, oops, there it comes. It brings up a, where's the mouse? This wireless display filter expression box that has all of the possible filters you can apply. So before it was a very limiting list, now it's almost too much of a list, too much information. But any possible filter, you can find the right pieces here. And the cool thing about Wireshark is every single field, every single piece of information it knows about, you can filter on. So if you are dealing with, for example, let's go with HTTP, it's common. If you're dealing with HTTP traffic and you want to create a filter, you can find the protocol, and then you can see all of the different things that it knows about HTTP. And it's all of the different headers that HTTP provides. They accept header, accept encoding, different forms of authentication, whether it's doing chunking, all of those things you could then create a filter on. And you could say, well, show me something like HTTP auth basic. Okay, so I'm doing this http.auth basic credentials. This is a not so great way to do logins over HTTP. And so I select that, and then I can choose over here what I want that field to be. Do I just want it to be present? Do I want it to have a certain value that's equal to something? Do I want it to not be equal to something? Less than, greater than? We have all these different relationships we can apply to this field. And in this case, I probably just want to know if it's present. Are they using an HTTP auth basic header? And I want to see those packets. And so I'm just going to do is present. If I wanted to check for a specific value, I could do this equals, and then down here I'd put the value that I'm interested in. As I click around and change the field and the relationship, you'll notice down here it's changing the filter. And let me put my mouse down there. And so down at the bottom of the window, as I've selected the HTTP auth basic, it added it to my filter. If I click the equal sign instead of is present, it adds the equal sign, and you'll notice it changes the coloring to red because it's not currently a valid filter. It's missing what is it supposed to be equal to. It needs a value. And this isn't a real value that would actually come up, but so we put in some value over here, and down at the bottom, it's changed it back to being green. Green doesn't mean it's a good filter, that it's actually going to do what you want. It just means it's valid, that the syntax is correct. So whether it's actually going to give you what you want, that's a different thing, but is it at least the correct syntax? Okay? Go ahead. Yeah. So how did we even get here? There is a button over here on the right-hand side next to our bar called expression. And you click that and it opens up this expression builder. Yep. And so let me add back in. What did we have? We had maybe you don't know exactly what it is that you're trying to, the exact name of the field. You can search, and it'll show you all fields that have that text. And so I can search for HTTP. That way I don't have to scroll through and find HTTP and reselect what I had before. I want to find packets with the HTTP auth basic. Okay, once you have it built, you click OK, and it will add it to your expression, which probably isn't what you wanted. And so in my case, let's get my mouse over there so we can see it. It kept the old HTTP that I had there before, and it just added this to it. That's just something to keep in mind when you do the expression builder. Maybe you want to clear it out. Maybe you really did want to add it, and the expression builder will just add it to whatever's there. So I can just get rid of what I didn't need. You have to apply it. So I've got it all typed there, but it turned green. It hasn't actually done anything until I either click the little arrow or hit enter. So the arrow's over here on the right. If I hit enter, that does the same thing as the arrow, and that will actually then apply the filter. And this is nice, this is a good sign. We say there was no HTTP auth basic. And I guess it depends on what side of things you're on, if it's a good sign or not. If you're on the security side of things and you're verifying your network, you're saying, yes, this is a good thing. My users aren't using auth basic and giving away their credentials. If you're on the attacking side, this is a bad sign because now you have to work harder to get the user's credentials, right? So I think I have a slide. Yeah, let's skip that one. Okay. Need to get rid of the magnifying glass when we're on the slides. Okay, so we haven't gone over all of this, and this is actually by design, is first I want you to struggle with it and try and get it, and then we'll talk about how you can get it and how we can do these things easier than maybe what you've done so far. So make sure you've got the baseline PCAP file, and there should be at least one machine who we've captured traffic from that is acting as an SSH server. It is accepting connections over SSH. There's several UDP protocols that are showing up in this capture file. This MAC address shows up somewhere in the capture file and is associated with an IP address. What is that? See if you can answer these questions. Okay, and I'll give you a hint, is that filters might make your life easier in answering these questions. Yes, so let's see. Let's put a little... Let's do it this way. Oops. Someone put it on Slack? Okay. And I'll just keep this down here at the bottom for now with the URL. So HTTP Icarus, yes, you. Okay. So we'll just leave that down there at the bottom if you need. I'm going to use this time to wander around and see how you guys are doing with this. If you have questions, you can shout them out or raise your hand. And let's see if we can answer these questions. So go there and add now downloads slash what is it? SAINTCON 2017 underscore captures. There you go.
How do you doppelgang filters together? You just do that, or how do you get?
Yep.
Okay.
Mm-hmm. Can you turn my mic off when I'm wandering around down here? Thanks. Okay, so how many people want more time? All right, so most people are ready to talk about this. You're going to have to help me remember what my 3 questions are as we look at this. Okay, so first of all, we asked about the SSH server. What was the IP address of the SSH server, or something like that? Yeah, okay. Okay. 3.1, okay? So, here's that IP address, 192.168.3.1. Does this one here tell me that this is a SSH server? How did you guys figure out that this one's the SSH server? Okay, so what filter? Okay, so we can do a TCP port equals 22. And this works because usually, or the default or standard port for SSH is port 22. And so we can say, well, show me all the traffic where this is true. And let me bring back my magnifier. Okay, so TCP.port equals 22 will show me not necessarily all of my SSH traffic, but it'll at least show me all of the SSH traffic that's actually using port 22. And now I've got, some 2 IP addresses there. Make sure you've got double equal signs. And is it showing up green? Make sure you do enter and apply the filter. I've had that. And I've also had it, depending on what version of Wireshark you're using, I know some of the versions had some bugs where, depending on how you cleared the previous filter, it would actually lock up. And so that might be what you're running into. So, but we're not done with the question yet. We've found some IP addresses associated with SSH, but we need to finish the question, which one of these is the server? So how do we figure that out? Okay, yeah, so if you look over here in the info, it's showing us the SynACK, which if you're familiar with TCP connections, you'll know, and if you're not, that's okay, we'll talk about it for a minute. Anytime you establish a connection, it goes through this 3-step process of the client, the one that's establishing the connection, sends a SYN packet. The server responds back with a SynACK packet, and the client responds with a final ACK. And that's true of all TCP connections. The side initiating the connection, which we'll normally call the client, is the, sends the SYN, the other side SynACK, and a final ACK. So using that, we can say, okay, well, the source IP address, the 3.34, is the one that's initiating the connection. It's the client. It's sending the packet to the 3.1. It's sending it to the server. So our destination, 3.1, this must be our server IP address. Now that's not the only way you could have solved this problem. Who solved this problem a different way? Yeah, go ahead here. Okay, good. I was hoping someone would do this. So you might, instead of doing TCP.port equals 22, you might try a filter SSH, sort of like we did with HTTP, where you just put in the protocol and say, show me everything that's SSH. Now there's some slight differences here. You'll notice our TCP connection packets, the handshake, is gone. It's not part of that filter, which is okay. And if we look at the info here, we can make the same type of analysis. Our server is sending message, our client's sending message. Well, which one's the source? In this case, the 3.1, so our server's our 3.1 address. Our 34 is the source on this client packet, it's the client. Now, okay, so one of the differences is you don't get the TCP handshake and the closing connection packets if you filter by SSH. How about if they're using a different SSH port? If they're using, port 2222, is Wireshark going to magically know and does it look at the packets and understand, oh, this looks like an SSH packet? Or is it just using the port to do this filtering? Does anyone know? So it actually just uses the port number. So keep that in mind if you're applying an SSH filter and expecting it to capture traffic to your SSH server that's using a non-standard port like 2222. Okay? It's not going to find that traffic. Let's see if we can. So if down here in the list, there's this SSH protocol part of the packet. If you right click on it, you can go to protocol preferences and it lists the preferences right here, or you can click on open SSH preferences here. And there's some settings you can configure with your SSH protocol. So we get this nice window that I can't see half of it. And you'll see it has port numbers listed. And the port numbers listed are 22 and 29418. Okay, so if you know that you run your SSH server on some other port, or you know the server you're connecting to is using a different port, and you want Wireshark to be able to filter when you type in SSH for your filter, all you have to do is add it to the list here, and then it will start interpreting those as SSH. So if I want, 2222, the example I gave you, to be treated as a SSH traffic, I just add it to the list of ports. Yeah, well, depends. So Wireshark has it in there for a reason and I'm not. Oh. Okay. Yes. Yes. Okay. I hadn't seen in my packet that was the client ephemeral port that was being used. Yeah. Well, thank you for verifying that. So yes, this will now provide a better list of 22 and 2222 will be recognized as the SSH ports, and you could, like I said, add any to your list that you need for the traffic you're working with. Profile. Yes, this is pretty much every single setting in Wireshark is profile specific. So if I change it here and then I switch profiles, it'll go back to its default, and we can even verify that. Right, so let's go ahead and click OK. And so instead of right-clicking on the protocol, you can also go to your Edit Preferences and find protocols in the list and find the protocol that way. It's more scrolling. SSH. So I've got my 2 here. They did save successfully. And now, if I switch my profile back to the default, if I check my preferences under my protocols, SSH, it's back to the original values. Okay. It's odd that that would be the, happened to be the ephemeral port. Oh, it wasn't even the ephemeral port. Okay. Yeah, so that's what I was thinking, is that it was probably in the list for a reason. It's not the standard SSH port, but it apparently would be one that is commonly used. Okay, so yeah, switching profiles changes these preferences. And I'm going back, just 1 second. Okay.
So say we can't see as much traffic as we want to see, how do we get to see more on our land?
Okay, that's a good question. Yeah, so the question was, back to capturing the traffic, what if you're not seeing the traffic that you want to capture? Right, that's what you're asking, right? So, get rid of my magnifier. If we come back to this picture here, there's a couple options depending on how much control of the environment you have. So if you don't have any control over the environment, there's not much you can do. Right? The traffic you see is the traffic you see. But if you can change what devices are here or how they're configured, you can then change what traffic you can see or change where you're capturing. So if you've got just a dumb switch here, a normal switch that's going to route traffic based on your MAC address and exclude N10 from seeing N12's traffic, well, if you can change this device or how it's configured to do like port mirroring and say, hey, everything that's going out these ports, also send it out this port so that N12 can see all of that traffic. Or, if you can either run Wireshark directly or run a capture software on your router and then send the traffic to Wireshark. So you'll see that done a lot where it's not Wireshark that's actually doing the capture. You'll use built-in tools on the router or whatever and dump them to a PCAP file and then load them into Wireshark. From an attacker's perspective, they have this same problem. They want to see traffic that they don't normally see. So there's Other ways you could go about doing it in terms of essentially you want to create a man in the middle scenario where you are, seeing the traffic in between two devices. And so there's techniques for that as well. Does that help answer your question? Okay. The other thing I should mention is you can get dedicated devices that will, you plug in the cable on one end, the cable on the other end, and then a cable running out to your computer. And so you splice into the traffic. Okay. The other thing I wanted to point out with using SSH and making sure it was clear of why it matters of, with the port numbers and setting those port numbers is from a security perspective. If you're expecting to find all of the SSH traffic by simply applying this SSH filter, your expectations are going to be incorrect. All they have to do is use a different port number and you won't see it when you do your SSH filter. Okay, Wireshark doesn't have some magic built in where it's doing a deep analysis of the packets and saying, oh, this looks like an SSH packet. Other questions on SSH? Yeah, so there's well, let's take a look. Where's our... So it's common for your server to announce what version of SSH it's using, that kind of stuff. And so you could filter based on those values. And you could, even if you, so we could filter specifically, SSH protocol, right click on that, apply as filter, show me all the packets that have the SSH protocol field set to drop bare. Well, that's still relying on Wireshark first recognizing what an SSH packet is. But if we change this to, and I'd probably mess up the exact syntax here. Maybe we can get it. Frame contains. Sweet. And I'll bring my magnifying glass so you can see it. So I can filter on the entire frame, that is the whole packet, and instead of filtering a specific field, I could look for specific text, specific data. And so I could say, well, if it contains this text, now I don't have to know that it was actually SSH traffic or that it was using port 22, but anything, whether it's on port 22 or port 622 or 22222, if it has this data in it, it will be picked up by the filter. Yeah. If it contains this whole thing, it would also contain just SSH. And so you could, do more or less based on what you were looking for.
What would you see as a protocol if it was using something other than 1.2?
Oh, okay. So that's a good question. It would depend on what port number it was using and how Wireshark was interpreting it. So if it was using a port that's commonly associated with some other protocol, it might try and interpret it as that protocol. If the packets were different enough that it couldn't interpret it, then you'd get some different behavior. So it's usually based off port number, but it's not a guarantee. in terms of what you would see listed here. Okay. So let's look at the next question. And, oh, what did that do? So what UDP protocols are used? What did you guys find on that one? Yeah. Okay, DNS, DHCP, MDNS. Was there any others people said? Okay. How many of you used some sort of filter to find that information? Okay. What sort of filter did you use? Makes sense. Looking for UDP traffic, we could apply a UDP filter. But this doesn't give me the answer. This shows me all of the packets, but I still have to go through and find the individual protocols.
I just sort it by protocol and just look for, oh, that's something new, oh, that's something new. And that's probably a better way of it.
Yeah, but so these fields are sortable. And you could say, well, right now they're ordered by their arrival, and instead let me order them by their protocol. Now they'll all be grouped together, and it'll make it easier to go through that list. And that's a great approach for answering this question. How else did people answer this question? Okay, yeah. So let's look at some of the other options that are available with Wireshark here. And again, we're just scratching the surface of what we can do. But we can come under statistics, and there's a whole bunch of different options. The one that's going to be most useful for us answering this question is probably the protocol hierarchy, which I think that's what you were saying as well, right? So if I click on that, it separates out all of my packets by protocol in a hierarchy, where it says they're all frames, 100% of them are frames, 100% of them are Ethernet, but 0.2% of them are IPv6, and 99.8% of them are IPv4. Well, what we care about is of those IPv4 packets are UDP, and we have this list MDNS, DNS, and the Bootstrap protocol, which is our DHCP protocol you guys mentioned. You'll notice this list, where's our SSH? Where's our HTTP? I know those are in the capture file, we just saw them. How come they're not in this list? Yeah, they're on your list, but they're not on my list. I've got a filter going, and the statistics are going to be based off of that filter. You'll notice, like I said, we won't go through all of them, but hopefully you'll take some time to look through the different statistics options. Wireshark isn't consistent in terms of when it applies the filter to your statistics and when it doesn't, but when it's not applying the filter, there's almost always a checkbox down here that lets you say either apply or don't apply the filter. And let's see if we can pull up one of those. Right. So for example, I just pulled up the endpoint statistic, and you'll notice down here there's a box that says limit to display filter. So the default list of endpoints is all of the packets. Even though I have a filter, if I want it limited to that filter, I have to check the box. So watch out for that when you're getting your statistics, is if you have a filter applied or not, and if it's counting in your statistics or not. If there's no checkbox, it is using the filter. If there's a checkbox, then it depends on if the checkbox is checked. Okay, so, all right, we did the UDP question. What IP address is associated with this specific MAC address? What'd you find? Okay, 192.168.3.232. How did you find that? Okay, so you filtered by MAC address. Yeah. So you can do, it's not going to let me copy it. I'm going to cheat. Okay, so I'm going to cheat, but it's actually a good thing because it'll show you other ways to build your filters. I didn't want to type in that MAC address. If you know what you want to filter on and you find it somewhere, you're like, oh, this is the value I'm looking for, this is the thing I want to filter, you can right click on it down in the list. So if I find it is cheating, right? I told you I was going to cheat. So this is the source address. I can right click on it, and there's, let's get a little more room there so it'll show up in the menu. Okay. There's two options that are good for your filter. You can either apply it directly, or you can just prepare it, which will build it but won't actually apply it yet. And in this case, I just want to apply it directly. And so I'm going to choose, so I right-clicked on my MAC address, and I'm going to apply as filter, and then you can choose how you want to filter. Do you want to filter everything that has that value, that doesn't have that value? Do you want to build onto your existing filter and add a and this thing, or an or it's and not, or not, right? So you can build them as you go, which is really nice. You have to be careful though, because sometimes what you select isn't quite what you meant. So before, in our example, you were saying to filter f.adder, right? ADDR, and put it in the address. And then I cheated, and I came down here and I clicked on the source address, and I said, well, apply this as a filter. Well, it applied it as a filter, but it's filtering specifically for that address as the source address. And so you'll notice all of these have the same source because it's filtered by your source address. If I want just the address in general, not source or destination, then I can change it to the adder. And now we see both sides, because in one it's the source and in the other one it's the destination. Okay. How about if we change this back. So I've changed it back to filtering it as a source address, but we haven't answered the question yet. I mean, we did answer the question, but we haven't seen the answer. I have this MAC address now. How do I find out which IP address it's associated with? I can either line up, filtering by source makes it easy, because now I know I just look in the source column and that's the corresponding IP address. When I do it by address, Now, if I'm just looking here, I see both those addresses, and I have to select one of the packets, which I've got, this one selected currently. And then I have to come down here and say, well, is this the source or the destination MAC address? It's the source, so it's my which MAC address? It's going to say, yeah, I was working on the wrong MAC address. We want the 2E MAC address, so it's the destination, which is so we come up with the destination IP address of 232. It's showing IP addresses. Let's switch our filter for a second. I'm going to filter to ARP packets. ARP packets don't have IP addresses. They are at a lower level in our networking OSI model, and they communicate on the data link layer. They don't use our networking layer, so they don't have an IP address. In this case, it automatically switches the source and destination over to be the source and destination MAC addresses. Depending on settings, you might have the actual MAC address, or you might have the named MAC address. And you can, change those settings. I think under our, actually, it doesn't look like it's listed there. It's under our name filter instead. So if we go into edit preferences and do name resolution, and so I've got the box checked that says resolve MAC addresses. That's how come, here I'll put my mouse over in there. That's how come I get a partial name with the MAC address, because it's using those first 3 bytes to identify the manufacturer based on its list, and putting that manufacturer name instead of the bytes. If you uncheck the box, then you just get the actual MAC address. You can do the same thing with these other addresses. So you can have it resolve your transport names, and instead of showing port 22, it'll show SSH. And you can resolve network IP addresses, and instead of showing an IP address, it'll show you the domain name. A caution on that, especially if you're capturing traffic on a network, is the way it resolves IP addresses is through the domain name system, DNS. It will actually send out requests, queries for all of those IP addresses. And so for large capture files or on networks where you want to remain silent, turning this on is a bad idea, because it's generating, Wireshark is then generating traffic to resolve these IP addresses. You can do some cool things though when you resolve IP addresses, in terms of you get the actual domain names. You can turn on geolocation if you download a GeoIP database, and then you can get a map of where all your communication's coming from. So there's fun things you can do with it, but do be aware that it is, if you turn on resolving network names, it will be generating traffic. Okay, what if you want the MAC and destination, source and destination MAC addresses listed here, even when you're looking at IP traffic? So let's go back to, maybe we'll filter for HTTP traffic. And my source and destination go back to being IP addresses. We can add columns to this list. And so we can come into our column preferences and add columns that way. For me, I always find that harder because then you have to go in, select the preference, protocol, add it. I'll click the little plus button, add it. I'm going to remove it because I don't want it. Oops. The easier way for me is just like I cheated with my filter, I can cheat excuse me, when I want to add a column. And at the top of my list is apply as column. So I can come up here, apply as column, and now I get a new column over here that is my source MAC address. And I'll line that up with my source IP address. And now it becomes much easier to answer that question of which IP address is associated with which MAC address because I have them listed side by side. All right, any questions on any of these that we worked through? Okay. And get rid of our magnifier again. So let's look at another feature of Wireshark called coloring rules. Coloring rules are a little bit different than display filters. Display filters actually change what's visible. Coloring rules are going to leave it all visible, but it's going to let us highlight things we're interested in. So maybe we still want the big picture of what's going on. We want to be seeing all the traffic, but we want to be able to easily hone in on specific areas of the traffic or specific features of our data. We can do that with coloring rules. And again, I recommend using these generously and using them specifically in different profile configurations. So on my machine that I regularly use for Wireshark, I have several profiles. I have one for HTTP analysis. I have one for ICMP analysis, and one for targeted attacks. And each one of them has a different set of filters and a different set of coloring rules to make the information I'm interested in for that type of traffic stand out. You might have noticed already, let's clear my filter, that Wireshark is coloring things differently. It's coloring these kind of a greenish color. There's some yellow, some blue, black, red. It's already using colors, but it's the default colors of Wireshark. Maybe I want something more specific. I'm going to create a new profile. And I'll call this one HTTP. And in my HTTP coloring or profile, I'm going to set up some new coloring rules. It depends on how you create it. So in the one where I just did and I clicked the new, it creates it based off the default protocol. If instead you go into manage profiles and you click the copy button, then it'll start with your whatever profile is selected as the base for the new profile. Okay, so if I go to view and coloring rules, we can see all of the coloring rules that Wireshark's currently applying. And bring our magnifier back. Okay, so it has rules for problems with TCP. It has rules for ICMP errors. It has different colored packets for different types of protocols. Yellow for the ARP, pink for the ICMP, which is commonly our ping stuff. More errors. HTTP is the greenish, which is why we're seeing that in the background there. Okay, so if this is my HTTP protocol or profile, maybe I want to add a new rule. And I want to say, I want to know when there's a file not found error. And when I get a 404 on my HTTP request. So I'm going to create a new coloring rule. And you'll see that it uses the display filter syntax, which is really nice because it means we don't have to learn something new. What we already learned with display filters applies equally well to coloring rules. Anything that would be filtered and displayed in a display filter, we could also say, hey, instead of changing whether you show this or not, just change how you color it. So maybe I want to filter HTTP response code equals, or let's say greater than 399 and HTTP response code less than 500. Okay, so I don't want just 404 errors, but 403 errors, any other 400 level error, I want to color the same. So I've got my rule defined. I still need to define my colors. And right now, my colors are a white background with black text. And I need to name my rule. So if I click over here where it said new coloring rule, now it lets me change the text, and maybe I'll call this one HTTP client errors. Down here at the bottom is where I change the actual colors. So it's currently, and this one always confuses me a little bit, because the background of the button is black and the words foreground are white, but it's the black that's going to be the color of the foreground. Same thing here, the background is white, the text is black, it's the background of the button that's going to be the background. So even though we use foreground and background, it's always the background color of the button that's actually applying to that item. So I want this to be, this is my foreground. Let's go with like well, let's keep the foreground black. Yeah, we'll go reddish. Indicate an error type condition. So I can specify, I click the colors, set the color values, however you want to choose them. So I'm going with the red foreground, and you'll notice that changed my text to red. And let's go with a yellowish background, because it's not a complete error, but a warning type that we want to pay attention to. Okay, so that's kind of an ugly yellow color, but whatever. Now I've got yellow background, red text, and if I have any 404 errors or any 400 level errors in this capture file, they'll be displayed right along with all the other packets, but they'll be colored with this yellow and red coloring. So I'll go ahead and click OK. And it should have started coloring those. So this is one that I have seen. I talked about there's a bug with the application of filters. There's a bug with coloring rules of when you set them on an existing file, it doesn't always reload them. Sometimes it does. But I'm just going to... Oh. That could be the problem. So let's go back in there. Sure enough, not checked. All right, blaming the software when it was my own fault, right? Oh good, I still get to blame the software. Didn't change it. Where's my 400s? Now it should change it. We'll see. http.response. Close 404. Oops. Okay. So then we see, right, all the 404s are showing up bright yellow and red. And let me clear my filter. And the nice thing is that we can still see those within the context of what else was going around. And we don't have to filter and only see those 404 packets. We can say, oh look, this one was fine, this one was fine, this one not so much. This one not so much. This was I told you the coloring rules. When you create them and apply them, there. And you have something selected, sometimes coloring gets a little off, but now it's all shown up. And this shows actually some quite nice context of, we didn't just get one 404 error, we got a whole list of them, all right. Oh, we're sorted by something. There we go. That's better. Over here on the far right is kind of a macro level picture of all of your colors. And so if yellow is hard to distinguish from green. If you chose a slightly more prominent color, you could look over here and you'd see, and you can kind of see like right there is probably a yellow stripe. And that can help you look for problems and say, okay, where are my 404 errors? And as you scroll through, you see the colors over here on the right changing and updating based on where we currently are. Yes. Yep, that's exactly what it does, is it applies the coloring rules in order of the first one that matches. So if a coloring rule is at the very top and it matches, it will apply that one, and then it stops looking at all of the others, and it won't try to apply anything below that. If it gets through the whole list and there was nothing matching, then it'll use the default color, which is probably white and black. So the order does matter on your coloring rules. And a great example, we have this one right here. We just did the HTTP errors. If we go back into our coloring rules, if we put this one below HTTP, now HTTP is always going to match a packet that it's also HTTP response code, and so we'll never see a yellow colored packet because it'll get matched by this green colored packet first. And we can verify. Filtered back to those 404s, and they're just the green with the black text. So order matters, and you should think about that when you're creating your filters. Okay, so here's another you try it. Get rid of our magnifying glass. Same file. Let's color all of the SSH traffic and color all traffic on port 443. And how you want to color them, red, blue, green, purple, whatever, I don't care. Just create some coloring rules. Should be under, if you go to view, yeah, and then coloring rules. There you go. Yep. Yeah. Okay, any questions on coloring rules? So it's for things like this is why I recommend creating those demo profiles, because if you're anything like me, when I'm just in a hurry creating some coloring rules, I end up with ugly colors that I don't want to keep around. So hopefully you did that in a demo profile that you can just throw away. All right, so we spent a ton of time talking about the interface, and we've looked at a few things that you can do to customize the interface and some of the things you can learn. Now let's actually use Wireshark to analyze some protocols. We answered some questions with it, but let's go into more detail on different protocols and things that you might be interested in learning when you're looking at your traffic. We'll cover these protocols in different levels of detail. Ethernet as our layer 2 protocol, ARP to help manage network addresses and MAC addresses. We'll look at our IP protocol. I think these baselines are almost 99% IPv4 traffic, so we'll mostly focus on that. ICMP, UDP, TCP, HTTP. There's tons of other protocols, and like I said, this isn't so much a let's learn about these protocols as a let's learn about how to look at these protocols with Wireshark. Okay, so we're back to this network picture. If you remember, we said you can only capture what you can see. How do you know what you can see? Well, to know that, you have to understand the protocols that are at work and how our networks are working. So if, assuming these boxes are switches, they route, well, they don't route, they direct traffic based off the MAC address if we're using the Ethernet protocol. What that means is that they look at that packet that comes in and they look at the source address, the destination address, and they say, oh, this destination address is on this port. It's on this line. And it sends it to that device and none of the others, right? It doesn't look at the IP address. Our Ethernet protocol and our routing at our layer 2 switches, they don't care what the IP address is. The IP address can be anything it wants. All it does is it looks at that MAC address and says, is this in my table? If yes, send it to this port. If I don't know about it, send it to everyone until I figure out where to send it. So let's look at ARP in conjunction with Ethernet. ARP is our address resolution protocol, and it's the way that we take an IP address and we find a corresponding MAC address. And we say, hey, I'm, back to our network picture, I'm this computer, number 12, and I know I need to talk to the IP address of my intranet server. Well, to do that, I have to go through my router, my default gateway. So it's going to say, I need to know the MAC address of my default gateway so that I can send a packet that the switch can understand and get it there. ARP is how we're going to do that. We're going to say, I know the IP address of my default gateway because it was provided to me through DHCP or it was configured statically or whatever, but I don't know the MAC address. So here's this IP address. Who has the corresponding MAC address? Whose is it and what is it? That's what ARP does. So normally we see this process. Send out a request. Who has this IP address? We get back a response. Oh, that's me, and here's my MAC address. Sometimes we see what we call gratuitous ARPs, where no one asked for the IP address. We're just announcing to the world, in case anyone's wondering, I have this IP address, and this is my MAC address. And we call that a gratuitous ARP. So let's pull up your baseline capture, filter so that you're just looking for ARP packets, looking at ARP packets, and then see if you can identify the normal request response pairs versus the gratuitous ARP packets. Okay, so I've filtered to my ARP protocol, and I come up with a list of packets. And down here at the bottom it tells me, 34 packets, or 0.1% of my packets are ARP packets in this capture file. And as I look through those, I can see this request response pattern that I talked about. And so we see a request from our 551D-A8 MAC address, and it's looking for IP address 3.1. This is the exact scenario we described in the picture of we were looking for the gateway router's IP address. 3.1 is our gateway router. And so 3.34 is trying to communicate with it. To do so, it needs to know what MAC address to use, and it sends out this ARP request. The good news is the very next packet is the response. And it says, 192.168.3.1 is at this MAC address. Now, Wireshark is providing this info summary. This isn't what's actually in the packet. If we look at this ARP protocol, what's actually in the packet is all of these bytes down here. And they all have meaning. And if we expand out our address resolution protocol and click on these different fields, we can see what the meaning of each of those bytes are. And so we can say, oh, this 0001, it means something. It means that we're using Ethernet addresses, that our hardware type is Ethernet. ARP can be used with lots of different data link layer protocols. Same thing, it could be used with different network layer protocols. So our next 2 bytes, this 0800, which is indicating that the network layer protocol we're trying to resolve an address for is IPv4. And then a byte to say how big the address is. MAC addresses are 6 bytes long. IPv4 addresses are 4 bytes long. So Wireshark provides a nice summary telling us what the packet means, and it provides us the actual details of what the bytes are and how to interpret those bytes. If I wanted to say, I don't just want to filter ARP packets, I want to find out the replies so that I can actually match up IP addresses and MAC addresses. We could do that, and we can apply this as a filter. And so I can do the opcode equals 2, which Wireshark's telling me is a reply, and now when I filter that, all of the packets I see are replies. And I can use this for troubleshooting problems and saying, look, why can't I talk to my router? Well, can I even figure out what its MAC address is? Do I see it here? Is ARP working correctly? Or is that where things are broken? And that's what Wireshark lets us do. It lets us see exactly what's being sent on our network. It lets us drill down and say, here's all this information, just show me the ARP, just show me the replies, and now here's my list of devices, and here's their IP addresses. Okay? Do we see any gratuitous ARPs in this capture file? What's that? Okay, so yeah, if where is that? Right here. All of these replies, they're replies to a specific destination. Right? Someone asked the question, who has this IP address? And then we're sending back the answer, so we're sending it to a specific location. The gratuitous ARPs, which we could quickly go through the list. All of these appear to be replies, and we could verify that with a filter. So we could say, well, show me all of the opcode 2 and ether adder equals FF. Oops. So that's our broadcast address. That means send this to everyone. And we see there are none. We do, let's clear my filter. We'll keep it, go back to filtering just ARP. The questions, right, are, when we're looking for a particular address, you'll notice those are sometimes sent as a broadcast. In particular, this first one, we're saying, who has this IP address? I'm interested. We don't know who has it, so we send it to everyone. And the way we do that is through a broadcast. On this one, when we are asking about IP address 34, you'll notice it doesn't send it as a broadcast. It's sending it to the device that it thinks has that IP address. It says, I've already seen this before. I just want to verify that this is actually still correct. And so I'm going to send it to where I think it goes. And if they respond back, then that's great. And I don't have to flood the rest of my network by sending this packet to everyone. I can target it and say, you should have this IP address. Do you still? Right? Is it still yours? And if I don't get back a response, then I can go back and say, okay, well now let's send it to everyone and see who has this IP address currently.
Can you check the filter ARP dot is gratuitous, because that doesn't seem to work.
So
There is a filter for it, but it doesn't pick up for any of the broadcasts.
yeah, so in this capture file there is no gratuitous ARPs. Right, so that broadcast we saw wasn't a reply back.
Oh, okay.
It was a question out, and those can be broadcast. So if we do opcode equals 1, that will show you all of the requests. ARP.opcode equals 1. Right, so doesn't have to be a broadcast because they can be sent targeted. Okay. Other questions about the ARP protocol or the things that we can look at with Wireshark in relation to ARP? We're building from the foundation up in terms of our protocols. So if we're thinking about using Wireshark from a troubleshooting perspective, we're saying, what's the communication at the lowest level? It's Ethernet and ARP. And so if we were trying to troubleshoot a problem and we wanted to take that approach, a bottom-up approach, and say, well, can I at least communicate to my router? Can I at least figure out what my router's IP address and MAC address pairing are? ARP is the place that we would look for that. From a security perspective, ARP can be useful for detecting man-in-the-middle attacks and ARP poisoning or ARP spoofing. And so we could use our ARP filters and say, is this information matching what's in my records? Right? Are the IP addresses shown here matching the MAC addresses of my devices? Or is someone else on my network pretending to be my router and trying to man in the middle that way? We probably won't have time today, but there's, in the capture files you downloaded, there's an advanced section, and one of the capture files, well, two of them are related to ARP. So in the Fates folder, there's this MacOff flood, and that has some interesting ARP packets. And there's this man-in-the-middle ARP poisoning capture that also has some interesting stuff going on with ARP. Okay, so let's keep moving up the chain and start talking about the IP protocol. Similar idea, we're going to load our PCAP file, same one we've been working with. Now let's filter to IP traffic so that we only see traffic that's involved with this protocol. And let's look at some of the things that go wrong with IP traffic. So we're going to look at fragmentation, we'll look at time to live, we'll look at different IP options. Okay, so I can apply an IP filter, and now all of my ARP packets are gone. They're not displayed, right? Because they operate below that network layer. And when I want to troubleshoot what's going on at the network layer, I've already looked at ARP, I'm done with that, I'm ready to look at my IP packets. So one of the things that happens with IPv4 in particular, IPv6 doesn't suffer the same problem, is fragmentation. That is, our packets, as they travel through the network, they might have to be split up into smaller packets. And the IP protocol has a way of dealing with that, and it does it through a couple fields and a set of flags. So if I expand out the details on my IP header, I can see things like, oh, it's IPv4 because it's got the 4 set, it's 20 bytes long, there's all kinds of information. But the ones that are interesting from a fragmentation perspective is this identification field. So each IP packet gets a number, and if that packet gets fragmented, it keeps its same number so that we know at the end how to put it back together. Say, oh, all of the packets that have number hex 9108 they were originally all the same packet. This particular packet has a 1 in this field right here that indicates don't fragment. So we know this one hasn't been fragmented because it's specifically been designated as don't fragment, which means if it's traveling through the network and reaches a network segment that it's too large to travel on and it would normally have to be fragmented, instead, if this bit's set, it'll drop the packet and it'll say, well, sorry, it's too big to go on this network, and you've told me I can't split it up, so the only thing I can do is throw it away. This is a great way for things to go wrong. If you're working on this diverse network with the different network segments, and you need fragmentation to get it across, and you've set don't fragment, well, now your packets aren't going to be reaching your destination. And you'll be going, what's going on? Because sometimes they might, if it's a smaller packet, and then you try and send a larger one, and it drops. Right? Most IP packets will actually have this bit set because it's much more efficient. If you don't have to worry about fragmentation, you can just send the packet, makes it faster to route things. And so it's common to see it set, but it also can be a source of your problems. These other two fields, our more fragments and our fragment offset, go back to helping put the packet back together. So if a packet gets fragmented, we're going to keep track of where it got fragmented. And we call that our fragmentation offset. How many bytes into the packet is this piece? Well, this one's 0 bytes in because it's not fragmented. If we had a 1,000 byte packet and we split it halfway at the 500th byte, the first piece would be offset 0, and the second piece would be offset 500. And that's nice because if later we have to further split that packet into offset 500 and offset 700, we can do that because it's just the byte number in the packet. And when we put it back together, now we know exactly which piece goes where. Yeah, so jumbo packets actually end up being a little different because they use extra options. But it's, yeah, similar idea of you could actually come in and look at Wireshark and see, what's being set and why is this packet not making it. And our more fragment lets us know when we've reached the last one. Because if you get some number, packet offset 200 and 500 and 700, how do you know there's not a packet number 1000 coming? The way you know is when this is set to 1. Then you know, oh, that's the last fragment. Okay. This is one of my favorite fields in the IP header, is the time to live field. It's just a number. In this case, it's the number 64. But that number will actually change as it moves through your network. Every time it passes a router, the router subtracts 1 from that number. And so if you've gone through 3 routers, at the end it would have number 61, because each router will have subtracted 1 from that number. People do fun things with this, like figure out how far away the server is by specifically setting the time to live to a small value and saying, well, what if I just say time to live is 1 and try sending a packet? If it reaches the destination, I know that destination is on my same network. But if it doesn't reach the destination, well, it must have been further away. So I know it's at least 1 step away. Now I could send another packet with the time to live of 2. And if it reaches the destination, now I know it's 2 steps away. Well, what if it didn't? Let's set one with a time to live of 3. And we can progressively increase our time to live to figure out how far away a server is. This is exactly what the traceroute utility does. It sends out successive packets, each time incrementing the time to live field, so that you can figure out how far away your destination is. And using ICMP, it'll actually get back responses from the routers along the way if you haven't blocked them, and figure out not only how far away it is, but what router names are between you and the server. Okay. Let's see, was there one other one on the list? Oh, IP options. So we had this field up here that told us how long our header was, and it was 20 bytes long. That's a standard IP header. That means it has all the standard information that every IP packet has. You can have options in your packets, and if you do, this number would be bigger because you'd have more bytes for those options. Things like jumbo packets can be done through options. Things like source and routing can be done through IP options. Most of the time, you won't see options. In fact, if we filter for IP header length not equal to 20 bytes. Oh, this is a good example. See how it turned yellow on me when I put in this filter? It means syntactically it's correct, but it's likely not what you're expecting. And let's go ahead and apply it, and we'll see why it's not what we're expecting. So it's not what we're expecting because it includes, oops. Oh, guess we got away. Okay. It would include things like if it didn't have a header length field at all, then this would be included in that filter. The better way to do a not equals and usually get more of what you mean is to say not IP header equals 20 . And so you'll notice we did get a few packets. 48 of our packets had a different header length, and they had, an extra 4 bytes, which we can see down here. They have this options. In this case, it's a router alert option. And so the reason is because these are ICMP group management protocols, and they have to alert the router to that fact. Right? And so they're doing it through an IP option. Like I said, most of your IP traffic won't have any options set, so we can see with the filter. Every once in a while, you'll find an option. Questions about our IP protocol or things we might be looking for in Wireshark when we're dealing with our IP protocol? So one of the things you might do in terms of creating coloring rules is create a profile for when you're specifically looking at IP traffic, and then create coloring rules to match the first packet of a fragment, to match all of the middle fragments, and to match the last fragment. And then you can visually see a green packet, a bunch of yellow packets, and a red packet. And I got the first, I got the middle, I got the last, fragmentation's working. But if you saw a green packet and a yellow packet and no red packet, you'd know there's something wrong and it's with the fragmentation. Another good coloring rule is the time to live. If you're seeing a very small time to live, that's probably problematic. You don't want the time to live to run out. When it runs out, the packet dies. The only time you want it to run out is specifically when you're doing, the trace route type functionality. So there's one other thing, and it ties into the next protocols we'll look at with IP, and that is the IP header tells us what's coming next. So when we did a filter for UDP or a filter for TCP, how did Wireshark know what packets matched that filter? Well, the way they knew is by looking at the IP header and checking the type field. And each protocol gets a different number. And so UDP is number 17, TCP is number 6, ICMP is number 1. And this is just a few of them. You'll notice there's a whole bunch of gaps in between for all kinds of other random protocols. If you're interested, here's the whole list of all of the IP protocols and their numbers that have been assigned by IANA, Institution of Names and Numbers, something like that. Where's our IP? So this protocol field, hex 11, which is decimal 17, tells us that UDP is the type of packet that's being encapsulated in this IP header. This is something that you don't have to worry about in attacker spoofing in terms of if it's UDP traffic, it will have number 17. If it's TCP traffic, it will have number 6. The port numbers, like the SSH ports and stuff, those an attacker can change at will. But these numbers are fixed because it's how our IP stack interprets and knows what protocol to give it for interpreting the rest of the packet. Okay. Oh, I thought there were some in this one. So let's look at ICMP next for a minute. To do so, we'll have to use a different capture file. Maybe not. Is it just my baseline file, or do you guys have any ICMP packets in your file? Okay, I don't know where they went. That's okay. So let's look at in the advanced folder. Do this nmap SN baseline. The nmap SN baseline. So we can add that to our notes here. So we're working with nmap SN baseline now. And this one should have some, does it not? Okay. I wanted the one with the baseline mixed in, but let's see if this one at least has them. All right. We'll use this one. So nmap sn ping. And if you filter, because there's some other traffic, mostly ARP traffic in this one, it'll show you a whole bunch of ICMP packets. ICMP is our Internet Control Message Protocol. So it's the protocol that lets the IP protocol manage errors and do management queries. It's the protocol that ping uses. It's the protocol that traceroute uses or can use. And it's the protocol that you get error messages about if there's a destination unreachable, or if fragmentation is required, you'll get an error message if it dropped the packet. ICMP covers all of that. This capture file probably only has one type of ICMP packet. Well, two types, but essentially one. So it has the echo requests and the echo replies, or ping requests and ping replies. And they're simple ways of testing network connectivity. When you ping ping google.com, it sends out a packet. What kind of packets it's sending out? It's sending out an ICMP echo request. And it's saying, hey, I'm just sending you this packet. Can you echo it back so I can verify that the connectivity from here to there is good? And the nice thing about it is that because it's at the network layer, we don't have to worry about if it's a problem with something else. Is it a problem with the port not being open? Is it a problem with the service not running? It won't detect those problems. It'll only detect connectivity between you and the endpoint. And it's not perfect because the endpoint can choose to ignore you, in which case you might still have connectivity and they're just not telling you. But if you do get back a response, then you know there is connectivity from your device to the endpoint. So ICMP packets, they build on top of our IP packets. They have your source and destination addresses. They have the fragmentation and all of that as part of our IP header. And then they have their own additional extra information. A type, like an echo request or an echo reply. And you'll notice the number changed there from 0 to 8 and 8 to 0. They have identifiers, and this is the exact same identifier. It's just Wireshark showing it to you two different ways. So the identifier is 535D, or if you reverse the bytes, 5D53, and interpreted as a decimal number. When they're ordered this way, it's 21341, and when they're ordered this way, 23891. So the BE or LE, big Indian or little Indian, which side of the byte is the most significant value. Same thing with our sequence number. We can show it two different ways. In the case of it all being 0, we won't see that difference. We should see a sequence number that's not 0. Maybe. Oh, all of the ones in this packet are 0, but it works just like our identifier. Which way you order the bytes will change what the decimal value is. So some things to watch for when you're looking for problems with ICMP is error responses, and there's already built in to some coloring rules this ICMP errors coloring rule. And so it's already, Wireshark knows most people care about if there's errors here. And so it's created a filter to say, well, if the type is 3 or 4 or 5 or 11 or 1, IPv6 types 1, 2, etc., those are error packets. Those are things like the destination's unreachable or the fragmentation's required and we had to drop your packet. So as you're scrolling through and you see this black line with green text, you say, oh, here's my problem. It's because I can't reach that destination, and ICMP's telling me about it. Your application may or may not communicate that information to you. Questions about ICMP, or the things we might look for with Wireshark? Yeah. Okay, that's a great one. So if you look, and is that shown in the info or down here in the summary? Okay, so the question was, what does it mean over here, where you can't see on mine because I'm zoomed in too much, when it says reply in some number, request in some number. So this is pairing up your requests and your replies, and it's doing it based off of the source and destination address and the sequence and identifier values. And so it says there was a request in, let's make this a tiny bit more smaller, in packet 216 that matches this reply. It has the same sequence number. It was sent to the opposite source destination because now it's a reply instead of a request. And it lets you then match up where the request was with the reply. And so that number is the packet number over here. So I've got it filtered right now to only show ICMP, but you can see there is actually 5 packets in between these. So that's just a way to, if they're not filtered and they're not directly one right after the other, you can still match up the request with the reply. Yeah, so we can take a look at that. Probe 2. Okay, so if you look at probe 2 PCAP, yeah. So you'll see most of it's these nice pink ICMP echo requests and replies, but over here we see some of that black bars, and we might just come right down here, and sure enough, it's indicating some problems for us, like the destination is unreachable. So we see the type's 3, the destination's unreachable, and in this case, the code is 3, meaning it was the port that was unreachable. If it's an error packet, ICMP includes part of the original packet in the response so that you can match it up. So you can say, well, destination unreachable, what was the destination? What's the, where was I trying to go? And that information gets included after our ICMP header. We have another IP header. So this one, let's make this smaller. Right, we have this original IP header, and we have the one that's packaged up with the response. And it says, well, the original packet came from 3.232, and we were trying to reach 3.1.12 on port 43357. And that's where we're getting the destination unreachable. So I don't know, the lights all of a sudden came on. What's going on? Nothing? Okay, you guys like the lights on, or want them back off? Yeah, that's what I was kind of thinking. I checked my clock. I was like, maybe it's already 5 o'clock and they're kicking us out, but we've still got plenty of time. All right, that might be a little too dark. There. Thanks, RD. Uh-oh. Now coming back. Who's got the magic remote? Playing with my head. Where'd the slides go? Oh, let's see if there's a trace route. Okay. I'm not sure what happened to my ICMP packets in the baseline file. But the other one, the error we might see is the time exceeded, and that's given when your time to live expires. So you'd see a time exceeded ICMP error message in that case. Some of the common types, again, there's a whole list of all of the different types of ICMP packets you might see. 0 for echo replies, 8 for echo requests. Destination unreachable is 3, which we just saw. Time exceeded would have a type of 11. A good rule to turn on, a good coloring rule to turn on is unexpected ICMP type codes. You don't necessarily want to have to always go in and check every time you're looking, is there some weird ICMP code here? But if you just color it, anything that's not a ping request or a reply, a destination unreachable maybe, everything else, let's color, they're not errors necessarily, they don't fall into our existing error coloring rule, but they're probably indicative of someone doing something weird on your network. Often, when you're doing like Nmap scans to try and identify a operating system, one of the ways they identify operating systems is by giving it weird ICMP type codes and seeing how it responds to those, because different operating systems respond differently. And so it's a good way to say, I don't want to always have to be looking for these, but if I color them different so they kind of pop out, that way when I am analyzing traffic, I'll see, oh, something weird's going on my network. Let me look into this closer. All right. Next protocol on the list is UDP. So we saw UDP a little bit already in that we filtered by UDP. We saw that there's DNS, DHCP, MDNS. Let's look at a few more details here. And I'm going to go back to my baseline file. One of my favorite things about the UDP protocol, so it's what we call a transport layer protocol. It gets wrapped inside of an IP packet. But one of my favorite things about it is that they're relatively simple, especially compared to our IP protocol and our TCP protocol. If we look at the header values of our UDP, there's not a lot to it. We have source and destination port numbers, we have a length, and a checksum. And that's it. That's our UDP header. All we need to know is where it's coming from, where it's going in terms of ports, how long it is, and optionally, we don't even have to have a checksum. We can leave the checksum blank if we want. Optionally, we'll make sure that the data is good. There's a reason UDP is so simple. The reason is because we wanted a protocol that can be low overhead, right? That's easy to send and use and able to send data quickly. People talk about, UDP is good for when you're doing live streaming or when you're doing simple request and response. Because UDP is not so good if you need to guarantee your data makes it to the destination. There's nothing in here to help manage that. What happens if our packets come out of order? What happens if a packet gets lost? With UDP, we can't do anything about those. All we can say is, here's our data, hopefully it gets there. And sometimes that's good enough. Like with DNS. The reason it's good enough with DNS is because we're going to send a question and get back an answer. That's it. It's like 2 packets. If something goes wrong, well, fine. We'll just send the question again. We don't need a whole bunch of overhead to figure out that we didn't get a response. A few things to point out in working with UDP is just like we talked about with TCP and like our port number, port 22, just because we say, DNS here is using port 53, that doesn't mean it has to. Port numbers can always be configured. And so if you're wanting to find all of your DNS traffic and you say, I'll do UDP port equals 53, well, that'll find all of your DNS traffic that's using port 53. It won't find it if you're running it on a non-standard port. Questions about our UDP protocol? Okay. Yep. So I've got DNS, DHCP are 2 common protocols. SMPP, NetBIOS are some additional common UDP protocols, and their associated port numbers. Again, this is just the default port number. That doesn't mean you couldn't run it on some other port, and an attacker wouldn't be running it on some other port. These are usually TCP over here on the left. These are UDP on the right, typically. and again, a link with an entire list of all of the different TCP and UDP protocols. Well, not all of them, but a lot of them, and their designated port numbers. So before we move on to to TCP, let's look at our DNS protocol for a minute, because this is another one that's often a source of errors with our network. Why isn't something working? Well, a lot of times it's because we can't figure out what its name and IP address association is. So DNS is our domain name service, and its job is to map a name to an IP address. Like in this example, the name github.com to some IP address. Over here, let me get my magnifier back up. Just like we had the arrows with our echo requests and replies, we have arrows with DNS requests and replies so that you can match up, here's the request, where's the corresponding reply? Oh, it's right here in packet number 3. And if we look, the summary is mostly sufficient for for what we are normally looking for with DNS. We want to know what domain we're looking for and what the response was, but there's more information available in the packet itself if we need it. So we have a transaction ID that lets us pair up the request with the reply. We can actually make multiple requests with a single packet. So in this case, we're only making one request. That's why the question's 1. And we're only getting one reply. Sometimes these numbers will be more. A single domain name could have multiple IP addresses, in which case maybe we'd have 3 or 15. Or when you start getting 15, that's usually a sign of either it could be a like cloud distribution network. Sometimes those will have lots of IP addresses, or the others that have lots of IP addresses are botnets. And so that's a coloring rule that you might want to apply, is if I'm seeing more than 10 or 12 or 15 or whatever makes sense for your network, maybe color those, because something weird could be going on. So here was the query. It was for github.com. This type A here indicates that we're looking for an IPv4 address. If it's the type AAAA, so 4 A's, that would be a request for an IPv6 address. And here's our answer. github.com has address 192.30.253.113. Okay. Questions on DNS? Perfect. Let's go ahead and start talking about TCP. TCP is a very complex protocol, especially compared to UDP. We won't hardly even scratch the surface of all of the things that can be going on with TCP. We'll look at a few of them. We'll talk about the three-way handshake, which we mentioned earlier. We've talked about port numbers already. Retransmissions is one of the biggest issues we see with TCP, and figuring out why are we doing retransmissions, where are the packets getting dropped. Hopefully we're doing it with what's called selective acknowledgement, so we don't have to retransmit everything, and we'll look at how to find all of that information. So back in the baseline file, we can apply our TCP filter. And the first thing we notice is that what we talked about earlier. Every single TCP connection has to have this sequence of packets where it's establishing the connection. It's negotiating parameters, and it's figuring out who's talking, what their sequence number is, what their window size is. All of these different parameters have to be negotiated before you can send any data. So what it looks like, this one's a SSH. Let's see. Oh, so it's a TLS connection that we're looking at. So we want to, probably some sort of HTTPS request that's being sent here. Before any of the URL or anything can be sent, the very first thing we have to do is establish this connection. If you're not able to connect, this would be one thing to check. Well, is it something at the application layer going on, or is it with my TCP where I can't even go through this three-way handshake process? Coloring rules can be nice here. In fact, let's do this one on your own so that I can stop talking for a minute. Create a coloring rule for TCP SYN packets and a different coloring rule for TCP SynACK packets. And so that you can visually find the first two pieces of the handshake. And if you want, you could actually do all three, the SYN, the SynACK, and the final ACK packet. So, whoa, there we go. Let's see, coloring rule for our SYN and ACK packets. So for the first one, right, the SYN packet, what coloring rule or what display filter did you use for this coloring rule? TCP.flags. And then I'm assuming that SYN, what? Yeah. So I'm not sure if you have to set it to 1 or if just this should work. Yeah, you can also, instead of doing individual flag bits, you could say, I'm looking for one that has this pattern of bits, which would be the, what did you say, 0? Yeah, 002. And maybe I'll color these with a green foreground. Okay. And then let's do a new coloring rule. So how would I do the second packet, the SYN plus ACK packet? Yeah. So let me, while I'm here, and I'll type these and then I'll show you that you can cheat. So we're doing TCP flags dot SYN equals 1 and TCP dot flags ACK equals 1. Okay, maybe we'll color that one blue. Oh, and I forgot to check the boxes. So we check the box. Okay. Let's find another one because that one was highlighted. There we go. So our SYN's colored green, our SynACK's blue. Looks like our coloring rules are working correctly in helping us highlight that pairing. Right? So then someone mentioned that, well, couldn't we have just cheated like we always do? And we certainly can. We expand our TCP. We come down here to the flags. And depending on how you want to do it, if we want, this flag combination, we could do that and right click. Normally, so we can see the menu. So we've seen we could apply this as a filter. Well, you can also colorize by filter, and you could just say temporarily apply this coloring rule with one of these colors here, or you could say use this to create a new coloring rule. One of the other things we can do with TCP, because it establishes this connection, Wireshark, as well as the application, is able to follow the entire sequence of bytes. So it doesn't matter how many packets you send, how many come from the server, how many come from the client. Because we've established this connection, we can track all of those packets. And with Wireshark, we can make it very easy to follow those. If I right-click on any TCP packet in the top list, one of the options is this follow option. And if I choose follow TCP stream, now it pulls up this new window where all of the data from those packets are shown here. And this isn't that interesting of a TCP stream because it's looks like probably a HTTP S encrypted conversation. But it colors the one side of it red, the other side blue. So in this case, it's our client that's red, our server that's blue. And we can go back and forth and we can see that it wasn't like a single request and a single response. It's actually intermixed. The client said something, the server responded back. The client said something else, the server responded back. The client said something else, and so we get this red and blue intermixed. And we can do, fun things with this, like we could say, well, only show me the client side or the server side, or vice versa. We could save that data. We could save the ASCII data. We could save the raw version of it. When I'm analyzing TCP traffic, I almost always end up following the stream. And this is one of the features I use most often with Wireshark. As I say, look, I've got all this other data. I just want to focus in on what happened between these two devices in their connection. And so following the stream lets me do that. The other thing you might have noticed when you do that is it automatically applies a new filter. And the filter in this case is tcp.stream equals 0. And the number will change based on which packet you happen to click on and which set of communication it was. Maybe it'll be stream 1 or 2 or 3 or 10. But what it's done is after you follow that conversation, what you're left with in the window is all of the packets of that conversation and nothing else. So we see the SYN, we see the ACK, SynACK, ACK. Now is our HTTPS certificate negotiation. Then we get the actual data being exchanged. And finally, we get our connection closing. Just like we have a sequence of packets that starts our TCP connection, we have a sequence of packets that finishes our TCP connection. And so we'll usually see a SynACK from one side and a SynACK from the other side, and that'll indicate both sides are closing the connection. Most of the time, servers today will also include these reset packets afterwards, and that's just an efficiency thing, so they don't have to wait around for confirmation of the final act. They say, I've told you I'm done, and now I'm actually quitting. I'm resetting this. So when I teach, I've mentioned I teach this at Weber State. When I teach this to my students, a lot of times they get confused and they think this is a problem or this is an error, or this is something unusual because it's colored that way. It's bright red, it stands out. You're thinking this is maybe something weird's going on. It can be if it's not part of closing a connection. And when it's part of closing a connection, it's just normal behavior. In other contexts, it indicates something's gone wrong. If you try and open a connection and instead of getting a SynACK back, you get a reset, well, that means the server is actively rejecting those connections on that port. If you're in the middle of a conversation and you get a reset, again, something's gone wrong. That is an indication of a problem. But a reset as part of a SynACK sequence is just normal, expected behavior. Let's see if we have an example of some retransmissions. So Wireshark, in the bottom left-hand corner, there's this circle, and it changes color based on what information Wireshark sees in your capture file. Right now it's yellow, indicating there's some warnings, but nothing super serious as far as Wireshark considers things. But if you pop it up, most of these are related to TCP. And so you'll see, like this warning, and there's actually a whole bunch of them where packets were out of order. We were expecting one packet and we got another one. Is that necessarily a problem? No, as long as eventually we got the packet we were looking for. It does indicate that there's some congestion on the network, that there's not abnormal, but maybe unexpected behavior, in that normally whatever you send first, you expect to get there first, unless there's extenuating circumstances. A route change, congestion on the network, packets getting dropped or lost and having to be retransmitted. All of those might cause packets to arrive out of order. And the way it tracks order is these sequence numbers. So we said we're establishing a connection, we're negotiating parameters. One of the things we negotiate is where to start counting. And every single TCP connection, both sides of it have a number that says this is byte number 1, this is byte number 3000, this is byte number 7000, and we count. And that's how we know when something comes out of order, because its number is off from what we were expecting next. Yeah, so I got this one down here in the bottom corner. There's this circle icon. Its color won't always be yellow. Its color is based on the highest severity of note here. And so in this case, our highest severity is yellow, and so the button's yellow. You can look through some of these other warnings. Here's one that we were just talking about, connection reset. There's a whole bunch of packets where the connection was reset. Wireshark has said, hey, this is a warning. Maybe it's something you want to look at. Yes, if it's not next to a SynACK. These notes deal with keeping packets in order, retransmitting when necessary. So we get packets where we say, hey, we've already seen this packet. In fact, we saw it multiple times. This is what we call a TCP fast retransmission, where the original packet didn't make it to its destination and we're retransmitting it. Similar type of thing on the duplicate acknowledgements. They usually indicate that packets have arrived out of order or have been lost, and so we're saying, okay, I got packet number 3000, but I'm still waiting for packet number 2000. And I'm going to keep telling you that I'm waiting for packet number 2000 until you retransmit it. As you can see, there's lots of these. It's not a problem per se, but it can be reasons why your network's slow. So if you're troubleshooting and you're saying, I feel like every time I go to this site, it's slow, pull up Wireshark and see, is there a lot of dropped packets between you and that site? And are you getting lots of retransmissions, lots of duplicate acknowledgements? If so, that's one of the reasons why it's slow, because you're having to resend things, send it 3 times instead of just once. Let's look at one of these packets. If you click on these, it should take you to that packet number. Oh, it's because it's filtered out of my... Okay, so duplicate acknowledgements. Okay, so when you click on them in here, as long as they're not filtered out, it'll take you to them in the display. And so we can see, we get an acknowledgement, another one, another one, another one, all acknowledging the same set of packets, the same byte number that we're looking for. We're saying, I need 115404 next. What we hope also happens with these duplicate acknowledgements is an option. And the option we're looking for is this SACK option, and that stands for selective acknowledgement. And what that means is that even though we're saying we still need packet 115404, we can let the other end know that we already got packets 121116 up to 128256, so that they don't have to retransmit those packets when they're retransmitting this one. They can say, look, I'm missing everything from 115 onward, except starting at 121, 116, I've got those. If you don't have selective acknowledgements, that's going to be a reason why your connection's slow, because you're going to be retransmitting information that was already received by both ends and just wasn't properly acknowledged. Let's follow this stream. Okay. Oh, so here's a good example, right, of following a stream where it's not all encrypted, so we can actually see it. So I just right-clicked on packet number 1602 and followed the TCP stream. And what I get is the request, and then the response, another request, another response, all in plain text because it's done over HTTP. And I can actually see all of the data, right, that was sent between these two devices. And some of it was even, this is probably gzip compressed. What is that? Oh, yeah. So this, where it starts looking like garbage, it's because it's been compressed. All right, but all of that is beside the point of what I was showing with our selective acknowledgement. The time that we decide if selective acknowledgement is going to be used is in this handshake, our SYN and SynACK packets. And if you look at these SYN and SynACK packets, under the TCP section, there's some options where different parameters are being negotiated. And what you want to see is that SACK permitted is one of the options being set. And so we do see that in this case. And we can filter based on that. We could say, show me all of the packets that do not have TCP option kind equal to 4, and you'll notice we get a bunch of stuff that isn't our initial handshake. So maybe we want to say and, so of those, and TCP dot flags dot syn equals 1. And we actually see several connections. Let me actually check, because I think, oh, yep, sure enough. Where at least one side of the connection isn't going to be using the selective acknowledgement. And we've got this whole set of packets that the selective acknowledgement option wasn't set. And this would be, if it's a device under our control, this would be one where we'd want to go in and change the configuration so that it did selective acknowledgement. And we would likely see a noticeable improvement in how our network connections functioned. These are all, I'm just double checking, but it looks like they're all IP addresses that are outside of, so the ones under my control in this packet capture are the 192.168 packets. So I can't do anything about the fact that 68.168.184.57 doesn't want to use selective acknowledgement. All right. Let's look at one other issue with TCP connections, and that is the timing of these packets. It's one of the things that's easy to get lost when we're looking at a list, is the fact that not all of these packets arrived the same distance apart or the same timing apart. So I'm filtering, so I'm just looking at TCP. And you'll notice these are all arriving fairly close together. I mean, we're talking about, what is that, milliseconds apart, or less than milliseconds in some cases, that these packets are arriving. But in other places, the gap might be, seconds or tens of seconds between packets. And when we just look at the list, it's easy to forget that. We look at the list and say, oh, well, this one came right after this one, which came right after this one, and we forget to look over at how much time elapsed between those two packets. One change we can make is we can, we can go under the View menu and the Time Display Format, and instead of showing, so the default is the time since the start of the capture, we could instead look at time elapsed between packets. And so we could say, where's packets? Since previous captured packet or previous displayed packet. And I like previous displayed packet because that way, as I'm applying filters on just my TCP data, my timing doesn't get messed up by some random ping mixed in the middle of my communication. Now we can start to see, without having to do the math, the difference in time between these packets, which was in our tens of thousandths of seconds, and most of these are all, here's one that took 0.3 of a second instead of tens of thousandths of a second. And when we're just scrolling through the list, we wouldn't necessarily see that. And well, let's do it cheat so I don't have to remember exactly what to type. So there's a whole bunch of time information that's not part of the actual packet, but Wireshark includes in the information, and you can filter on this information as well. So I can say, well, time since my previous displayed frame, let's create a filter and say, well, let's find all of them that were exactly 0.43500 seconds apart. Well, that's not that useful because they're not likely to be exactly, but more useful would be, well, show me everything that was more than, 1 second apart, maybe. Okay, and this one's actually saying there was never a packet that was more than 1 second apart. Frame time delta displayed. Let's make sure this is actually doing what it's supposed to. Yeah. Okay, so in this capture file, which isn't that surprising because it's all done on a couple virtual machines where networking is going to be practically instantaneous, everything happened fast. Nothing took more than a second from one packet to the next. Oh, actually, let's do TCP and okay, yeah, so it's still happening fast. Yeah, this filter's not quite doing what it's supposed to. Let's try a different filter here. There we go, this one's going to work better. Because when you're, okay. So, if you can see, before we were doing time since the previous displayed packet. Well, that's problematic if you're trying to filter what packets are displayed. How's it going to calculate from previous displayed packet? It doesn't know which ones are displayed. And so, but filtering on our time delta, so time since previous packet, that works much better. But then we have to worry about extraneous, what happens when the packets are from two different sources and they're messing up our timing. There's other time values you can look at. So if we expand out, our TCP options, now we can say, show me, the time between packets in this TCP stream. So I don't have to worry about another TCP stream or a random ping or something like that. So we can say time since previous frame in this stream. And maybe I want to say, well, show me any of them that took more than 1 second. There we go. And the good news is almost all of those, if not all of them, are the last packets, right? Our SynACK packets. And that's normal for there to be a bigger time between those packets. And in fact, some of these are quite large, 22 seconds in this case. That's okay. Those time values aren't problematic. It means we were communicating with this client or server, sending packets back and forth, and then we were done, but we didn't close the connection in case we had more things to communicate. And we kept it open for 22 more seconds before we said, okay, we're really done, let's close this connection. So a long time with a SynACK is usually not a problem, but if you did this filter, TCP, time delta, and 1 second's not super long, but 5 seconds or 10 seconds, and it's the middle of a communication, now maybe that's indicative of a problem. Why is the server taking so long to respond? Why is the client taking so long to generate data? And it gives you an indication of where to look for the problem. The packet made it there just fine, but then the server sat there for 5 seconds before it did anything. What was it doing? Was it querying a database and pulling from a billion different records and that took 5 seconds? Or was it stuck in a while loop somewhere? All right, so we can look at HTTP next. Depending on some settings here, what you get displayed with HTTP will change. And I think under the default settings, which I should be using, it shows you when you make an HTTP request, it shows you that request packet, and the packet that it shows for the response is actually the last packet. So you see our get, and okay, those are our responses. So let me illustrate what I'm talking about here. So I've got this GET request. Let's not do that one because it's a 404. Let's do this one. Okay, so I've got this GET request with packet 5049 and this response 5095 as the response. And that's it. That's all it's showing me. It's not showing me all of the data in between those, if there was any data. So let's follow the TCP stream here. And we can see, yes, there was in fact 5049's right there. Right, so there's packet 5049 still. There's the HTTP response in 5095, but there was a whole bunch of, not a whole bunch, but some data in between that didn't get included in our HTTP filter. And it's because it's only marking the packets as HTTP if it's the actual request or if it's the last packet of the response. You can change that behavior with our TCP protocol preferences. And this allows subdissector to reassemble TCP streams. So if we uncheck that, now all of that data in between, so 5040, I can't remember which numbers we were at. I think this is it. 49, right, and 91. There we go. So what it's done is it's taken it gives us these packets in between where it says this is just a continuation of our HTTP data. I get stuck on this one of which behavior I prefer. I actually don't like either one of the behaviors. I wish they would let me have an in-between behavior. Let's switch that back. Okay. So I usually have the second box checked, allow the subdissectors to reassemble data. And then when I do that, I just remember that if I filter for HTTP, it's not giving me everything that's port 80. It's only giving me, it's only marking that first and last packet. And the reason it does the last packet is because it's reassembling the data in that packet. And so if I go to that example, which was somewhere there. Mostly I just want one that's not a 404. Oh, here's one. Okay. 549, that's the one I was using before. So in this last packet, 595, if I look at the details, it's actually reassembled all of those packets in the middle, and it's put them together here in one big packet. So the thing I don't like about this is now all of a sudden my packets are kind of lying to me again, in that they didn't come all in one big packet, but at least it does tell me, hey, these actually came in 4 different packets. But what I do like is that then it's all here in one response. And so I can see the entire response down here in the data. Okay. We can see the data, we can see the headers. Whoops. So we see, our status code, we see the HTTP headers, accept ranges, content length, all of those, and then we see the actual response data. Let's do one of the cool things you can do with Wireshark is under the file export objects, and there's different protocols here. The one that I use most is the HTTP one, because I'm rarely analyzing DICOM or IMF traffic. But if I choose this, export HTTP objects, then it gives me a whole list of all of the stuff that Wireshark saw that came over HTTP protocol, and it reassembles them into one coherent piece of data. And it says all of those packets that made up the request to security.cali.org, here is that data in a text HTML format. And hopefully there'll be one that's an image. Well, let's sort by content type. Now in this example, pretty much all the data it looks like was just HTML data or compressed data. But if you included, when you're doing normal web browsing and you download an image or whatever, it'll show up here in the list. And you can grab it and hit save or export, whichever the button says. My magnifier's in the way. Yeah, so you grab whatever it is, hit save, and it'll pull out that image. You don't have to go in and find all the bytes that make up the image. It does it for you. If you didn't get all of the bytes, it won't work, obviously. If there were, drop packets, or you started capturing halfway through the transmission, you won't receive the full image. But if you captured the entire process of packets from source to destination, when you export that image, it'll be the actual image, as if you had downloaded and saved it to your computer. Any of these values, the host, the user agent, cookies, the basic authentication, we talked about that at the very beginning, they all show up here. So if you're doing HTTP and you're using basic authentication, it's not encrypted. It shows up. Anyone that can sniff that data can grab those credentials. We saw this with cookies, not so much today. Most people have gotten smarter, but instead of using a session cookie and storing the information on a database or something on the back end, they'd actually just put the information in the cookie. They'd say, admin equals true or whatever. Well, all of that information, if it's HTTP, plain text, anyone can grab it, anyone can modify it, anyone can change it. You can follow the HTTP stream instead of following the TCP stream if it's HTTP. And let's look at an example there. So I'll just grab one of these. I'm on packet 641. If I follow the HTTP stream, it gives me what looks like very similar to when I followed the TCP stream, and it's almost identical, except so there might be some other differences. The main difference that I notice is if you're actually doing decryption. So if it's HTTPS and you have the key to do the decryption, if you just follow the TCP stream, it still shows you the encrypted data. But if you follow the HTTP stream, it'll show you the decrypted data. Just like we could calculate timing information with TCP, we can calculate timing information with HTTP. So for example, I have this request that was made in packet 590, the response in 599, and if I scroll down here, under the HTTP header, Wireshark adds this field, time sense request. And we can create a filter. We can show me all of the HTTP times greater than 1 second. And quite a few of them. This is the from start to finish of request and response. And if we say, well, how many of them took more than 10 seconds? And the good news is, none of them took more than 10 seconds. about 5 seconds. So we just had 2 requests that took more than 5 seconds. And neither one of them were super large, so that wasn't the problem. It was, likely, you'll notice they're both from the same server. So here's a nice example of how this can be useful. Everything else happened in under 5 seconds except to this one server where it, 2 of the requests ended up taking more than 5 seconds to get a response back, to get the entire response back. This will also change, this timing will change if you have it reassemble the packets or not. And so right now I rechecked it so that it is reassembling the packets. That will measure time from start to finish. If you don't have it reassemble packets, it measures time from the request to the start of the response, which is very different, but can also be useful information.
I've also seen similar things where you have packet capture in front of the load balancer, so one thing behind your load balancer is slow, and you're seeing this weirdness like this.
Yeah, that's a great point. One of the useful features of Wireshark is capturing at different points in your network and saying, what's the timing look like here versus here? And that can help you pinpoint, where the slowness is happening. Okay. That's it. We made it through all the protocols that we had scheduled to talk about. Any questions? All right. Well, those of you that are left, you're troopers. Way to go. I'm happy to talk to you if you have questions about Wireshark. If you have questions about other things, I'm happy to talk with you. SAINTCON is one of my favorite conferences because it's so personal. And you get to interact a lot with one another. So thanks again for coming, and enjoy the rest of the conference.